Chapter 16 is on constrained least squares. That's an extension of least squares that's going to allow us to add linear equality constraints to a least squares problem. And that really actually pulls together kind of the two things you know how to do. Solve linear equations, number one, and number two, least squares. And this will actually, it's like the common parent of both of them. Okay, so we'll start with defining what the problem is, and we'll talk a little bit about the nomenclature and that sort of thing. Okay, so here is the linearly constrained least squares problem. We're going to call that CLS for constrained least squares. And it's an optimization problem, and it is described this way. It's minimize the norm of ax minus b squared. Now, by the way, that alone by itself is simply the least squares problem. But then we have this, subject to cx equals d. Now, the variable here, which is the thing that we want to find or solve for or something or compute at some point, is this n vector x. So that's what this means. Now, what this constraint means, the semantics of it is this, is that we would like this to be small. So the smaller norm ax minus b squared is, the happier we are. The constraint says basically we will not consider any x that does not satisfy it. So if someone comes along and says, hey, how about this x? If cx is not equal to d, we're not interested. Okay? If cx is equal to d, then we say that that point is feasible. And then we'd say, okay, now then tell me the objective. And then, of course, if we have two of these and they're both feasible, one has a lower objective than the other, we prefer that one. So that's the semantics of an optimization problem. And this is kind of a standard form for describing one. I should say that this is not mathematical notation, or sorry, these are not like mathematical operators. Like min is a mathematical function that takes a finite number of real numbers and simply gives you the smallest of them. So this is actually really what we're doing is we're describing an optimization problem. Okay. So here the matrix A is m by n. B of course must be an m vector. C is a p by n matrix, and sometimes people would say this problem has p linear equality constraints. And the vector D is of course a p vector, and these are called problem data. The idea is that they're given, right? So you know them. Your job is to find x, but you know A, B, C, and D. Okay, now norm squared of ax minus b, that's called the objective function. So you've already seen that. That's the objective function. Cx equals d, people would describe as the equality constraints. And it says basically we will not consider any x that does not satisfy Cx equals d. Okay, now what does it mean to be a solution of this problem? To solve this problem, what we mean is two things. Number one, we'll say that the vector x hat is a solution if it must be feasible. It must satisfy Cx hat equals d. That's the point of the problem. And the following is true. For any vector x that satisfies Cx equals d, so for any other feasible vector, the objective of the point we are proposing, x hat, has to be less than or equal to the other one. And that's it. So it is the best, in terms of lowest, it's the least objective point among all feasible points. That's one way to say it. Okay. So what's kind of cool about it is it combines solving least squares problems. I mean, because part of it, I mean, this part is just least squares right here. And then subject to a set of linear equations. So it kind of glues together the solving linear equations with a least squares problem. Another way, a very good way to think of it also is it's a bicriterion problem. It's sort of in the limit of lambda going to infinity. In other words, if I were to form the bicriterion problem that looks, and I'm going to scalarize it now, so it looks like this, right? That's my objective. Now the meaning of this is that we'll allow Cx to not equal d, but we're going to penalize you for it. Now, as lambda goes to infinity, that basically is telling us that you have your only choice is to have Cx equals d. And so we would expect when lambda goes to infinity, this just basically, by objective least squares, is going to give you a solution of the constrained least squares problem, the CLS problem here. Okay. Now we're going to find out that in fact you can. We're going to find out that there's a direct method to solve directly the constrained least squares problem. But nevertheless, this is not a bad way to think of it. It is something like a bi-objective least squares problem as the weight on the second one goes to infinity, which causes it to basically become an equality constraint. So we'll look at a quick example. We are going to fit, let's say, some data or whatever, or points to a so-called piecewise polynomial. Piecewise means that you chunk up the function into, this is a function on R, a scalar function. So it says you chunk up R into intervals, and then on each interval the function has a particular form, possibly different coefficients. So what we're going to do is we're going to say that f hat is going to be the polynomial p when x is less than some number a. A is sometimes called the not point in such a model. Or it's equal to q of x. And they're both just cubic. They're just cubic polynomials, okay? But we're going to add some constraints now. And the constraints are going to say that we want, number one, we want f hat to be continuous. And that means that when we evaluate, when you jump from a little bit less than a to a little bit more than a, we want to make sure that the function value is the same. And so that would be this constraint. P of a is q of a. And the other thing is we're going to ask for the derivative to be continuous. By the way, we could also get the second derivative to be continuous there if we wanted. And so these are our requirements. By the way, when you have a piecewise polynomial and you make constraints on how many derivatives must match at each not point, the resulting function is called a spline. So that's something you'll almost certainly be hearing in whatever you end up doing, you're going to hear about splines. And so this would be a cubic spline of some kind. I forget what kind I forget how people call it. Okay, so what we're going to do now is we're going to fit f hat to some data, xi, yi. And we'll minimize the sum square error. And we're just going to express that as a constrained least squares problem. So this is going to be that's going to be, of course, our objective. And these are going to turn into, that's going to turn into our Cx equals D part, the linear equations or linear constraints part of the problem. Let me just show you how it works first. So there's some data points scattered here. Here's the number A, and the blue shows you P, and the red shows you Q. And what you can see here is, okay, well, number one, we solved it. We'll see how to do that later. You solved it, and actually, sure enough, both the blue P and the red Q fit the given data pretty well. But the really cool part is this. Number one, they match up at A. That's one of our constraints, and the second one is their derivative is the same at A. So that's and this is what it would do. If I didn't do this, right, the red curve could go up like that, and the blue curve like that, and there'd be a jump there. So that would be by imposing this constraint, I'm avoiding that jump. Okay, so let's see how to actually put that problem into that standard CLS form. Well, the constraints are P of A equals Q of A. That's P of A, and this is minus Q of A, right? So that's what that is. And it just says they're equal to 0. So P of A minus Q of A equals 0. And then this expression here is P prime of A. Because, P prime is this polynomial theta 1 plus theta 2a plus theta 1 plus theta 2x plus theta 2 3x squared. And you take the derivative and you get this. So that is this thing right here. That is P prime of A. And this thing here is minus Q prime of A. Okay? And if we look at this, we'll see that we could write these two equations as C times theta equals D. Theta is the 8 vector of parameters. C would have 2 rows, right? So in our constrained least squares problem over here, C we'd have P is 2, and that means that there would be 2 linear constraints. And in fact, you could even annotate them. The first one says continuity at the naught point, and the second one would say continuous derivative at the naught point. Okay, so that's that. And of course, the prediction error is easy to do. I mean, what you do is it's simply AI transpose theta minus yi, and AI is going to be either is one of these two things because you're selecting which polynomial you evaluate to fit the model. And then the sum square error is a theta minus y, norm squared. So this would this means we can easily we can put this immediately into this constrained least squares problem format. Now we don't yet know how to solve that problem, but we will. I mean, later you'll have some code, or it's going to be very short. It just gives you the solution of this. You pass in A, B, C, D. What comes out is the solution. That's it. Okay, so that's coming up. Before we jump into how you solve it, we want to look at a special case, which is actually fairly important. It's called the least norm problem. It's just a special case. It's a special case when A equals I and B equals 0. And so basically the problem looks like this. It says, find me, this is AX minus B, but A is the identity, B is 0, so it's just norm X squared. So this says, minimize the sum of the square, minimize the sum of the squares of the components of X, subject to X satisfying Cx equals D. Geometrically, that means find the smallest vector that satisfies a set of linear equations. So it's very interesting. Usually in many applications, somehow the size of X will translate into something like find me the most efficient solution or something like that. That's typically what it means. And this works, of course, when there's many solutions of Cx equals D. Let's look at an example of that. Very simple example. So I have a unit mass on a frictionless surface, and it's initially at rest. And then what we're going to do is we're going to have a 10 vector, F. And what it does, we're going to apply to that mass a force on it, each one for 1 second. So we'll apply the force F1 in newtons to this mass for 1 second. Right at 1 second, we're going to switch to the force F2 and that sort of stuff. Now, if you'd like to know what the final position and velocity are after the full 10 seconds, it's this. The velocity is just the sum of the forces, right? Because if I apply 1 Newton to a 1 kilogram mass for 1 second, it acquires a speed of 1, right? So, which is, that's fine. And if I apply a force F1, it acquires a speed F1, okay? So it's actually the sum of the forces gives you the final velocity. Okay. The position, you can work it out. It's not very hard, but it's equal to this. It's like 9.5 times F1. I guess that is 8.5 times F2, and so on, and only a half of F10, right? By the way, you might ask yourself, why is that? That's weird, right? And the answer is really simple. When I apply the first force I apply, I end up giving the mass a velocity, but it keeps that velocity for the remaining 9 seconds. That's why that works, right? And so in some ways, that first force I apply is much more efficient, right, in terms of how far you get, if that's your goal. It's very right. Whereas the last force you apply is right up to the last, and that only gives you a half. Okay. So anyway, this is easy to derive. All right. Now here's what we want to do. I would like to find a force sequence which causes the final velocity of the mass to be 0 and its position to be 1. So very simple. This is actually it's called in control. It's called transferring the mass. So the mass is sitting here at position 0, velocity 0, and after 10 seconds, I need it to be 1 meter to the right. That's what I'm taking 1 to mean. 1 meter to the right, and it should be stationary there. Okay, so that's my job. Okay, now there's a ton of force sequences that do that. Here's a simple example, right? If you apply a 1 Newton force, So you push it real hard. It'll accelerate after 1 second to a speed of 1 meter per second, right? It'll have gone half the distance, right? Then I instantly switch the force to, instead of full pushing, to full pulling. Now I pull the mass for the next seconds, and all I'm doing is I'm bleeding off the speed. I'm bleeding off the velocity. And so what happens is, over the next half a second, the velocity goes right down to zero. Right at the end of 2 seconds, the velocity is zero. And the position is 1 because I also move another half a meter. So I'm actually right where I want to be after 2 seconds. And then I just sit tight, and that means apply zero force for the next 8 seconds. Now, of course, what that means is that, if you apply zero force to something that's, zero velocity, zero position, it just sits there. Okay, so this is called bang bang, because the force goes up to a large value, then switch instantly down to the negative of that. Okay, and this comes up in a bunch of in a bunch of different things. Okay, but there's lots of other Fs. So here is the bang bang force sequence, and here's the position over time. Right, so this is, and it makes perfect sense. Like, how do you move something from here to here? First, you push it to get it going. Then that's this part, right? And then you pull on it to bleed the speed off, so that when it arrives at the final target position, it's stationary. It has velocity zero. I should mention something just for fun. Here are we're using the requirements that v final equals zero. But there are applications where this is not there. Okay, so I'll give you a rough idea about that. If someone, I can tell you exactly where this comes up. If this is something like a missile, or a bomb, right? Then what someone says is, get me to the target. You say, yeah, get me to the target. And you're like, sure, no problem. And then you say, by the way, when you arrive at the target, what speed would you like to be going? And they're like, it doesn't matter. Okay. So roughly speaking, when you see optimization problems where the final target specifies the position but not the velocity, generally speaking, these are not socially positive applications, but they have them, obviously. I just thought I'd mention that. Okay. What we're going to do now is we're going to find the least norm force sequence. So this is a solution of the problem. It's just this F satisfies our equation, which is just CF equals D. Now D just happens to be 1, 0. Okay, 0, 1. Sorry, there you go, 0, 1. Okay, but so this is one solution of this very much under specified or underdetermined linear equation. But we're going to see another one. And notice, just remember the number. It's 1 Newton and minus 1 Newton. What we're going to do now is set this up and find if you like, the gentlest force that transfers a mass 1 meter in, over 10 seconds. The gentlest force. And we'll define gentle by the sum of the squares of the forces, right? Okay, so here we end up solving this very specific least norm problem right here. And you can understand everything here. The first equation is telling you the sum of the f's should be 0. That's the one that says that when you arrive at the target position, you should have velocity 0. And the second one says you'll actually make it to the target. Okay. Now, it turns out that when we work out what that is, now you can work it out analytically, but there's no reason to do that. You just use the methods we're going to talk about later, and you can do it numerically. But here's what happens. You end up with a norm squared of the solution of this being 0.0121. That is compared to the bang bang one has a norm squared of 2, because it's 1 Newton and then it's minus 1 Newton. You square those and add them, you get 2. Okay, so this is, what is that? 200 times, quote, gentler. It's basically you're applying a force that is, if you care about the sum of the squares of the forces, it's 200 times smaller. That's not surprising, right? Because you obviously could do it a whole lot more gently than giving it a big accelerator. And besides, we're wasting this thing gets you there in 2 steps, but I gave you 10. So okay, so it's not surprising. Um, Now let's look at that force. Here's the force, and here we go. We go from position 0 to position 10. Notice completely different scale. That's 0.05 and minus 0.05. If you remember the bang bang force sequence, that was plus 1 Newton and minus 1 Newton. So this is 20 times smaller. Sorry, starts 20 times smaller and then gets even smaller still. Here's the interesting thing. Bang bang looked like this. On a completely different scale, it would look like this and then switch over, switch down to here, right? This would be at plus 1 and minus 1. But what you can see here is pretty cool. What it does is it starts by pushing it, 0.05, which is a whole lot less than 1, 0.05 Newton. Then in the next step, it's a little bit less, a little bit less, a little bit less. And then right at t equals 5 is when you switch over from a small push to a small pull. And then you pull a little harder and a little harder still. And so, and then by the time you get to the end, you're pulling, it's symmetrical. It's like, minus 0.05, you're pulling by 0.05 newtons, roughly, okay? And here is the trajectory, right? And it's actually kind of cool, nice and smooth. So people use force trajectories like this like all the time. I mean, this is very, very common to use these things because you can generate beautiful, nice, smooth force trajectories. So that is kind of the idea. Okay, so now we haven't yet said how to solve a constrained least squares problem or a least norm problem. That's going to be our next topic.